Good morning, everyone. So I have posted the first homework, but it's just part of the homework. So in the future, if you see if you see there is an updated on the title of the homework assignment, that means the homework is not finalized yet, because I have to wait until the next week to see how far we go. So then I can assign the corresponding assigned homework assignments from the corresponding sections. So usually I will finish it on Tuesday or Monday, as long as I have an idea of how far I will go in the following week. So far I have posted 3 sections of homework, which are all from chapter 6. So if you have time, you can start doing those assignments after our class. And right. So today we are going to talk about the work. The title of section 6.6 is the application of integral in physics and engineering, but we will only focus on the work done by a force. So the work in physics it's defined by this formula: W is equal to F multiplied by D, where F is a force acts on a certain particle or a certain object, and D is the distance travel, the distance that the object travels under the effect of the force. And this simple multiplication can only be applied to a constant work. Constant force, the work done by a constant force. But in this section, we will focus on the case when the force is not a constant. F is equal is a function of x instead of a constant. Then the work done by the force from A to B, from moving an object, so A to B. So it's from X to A and X to B, which means which represent the initial position of the objects and the terminal object, the terminal position of the objects. So force is given by an integral. W is equal to the integral of f of x from A to B dx. And the derivation of this formula is actually straightforward. It's nothing. It's not very different from what we did for the derivation of an integral. So suppose suppose this is the curve, or this is lowercase f. So suppose this is the force, the curve for the force f of x, and this is the initial position of the objects. This is the terminate position of the objects. Then although we can calculate the work directly by W is equal to F multiplied by D, but if we divide this this interval a to b to a lot of subintervals. So like x1, x2, and then so on. Then suppose there's an xi plus 1 here. And there are a lot of other subintervals here. So if we do that, then on each subintervals, because the subintervals it's small enough, so then on this subinterval, interval xi to xi plus 1, the force is approximately a constant. So approximately a constant. And just like what we did for the integral, we will pick a sample points from this interval and use that, use the value of the function evaluated at that sample points. Let's say this is xi star. Xi star. So we'll say that on this subinterval xi to xi plus 1, the force is approximately a constant, which is given by the value of the force evaluated at a sample point. Then the force done in this interval, so the force that moves the objects from xi plus 1 from xi to xi plus 1 is approximately Wi is equal to f of xi star multiplied by delta x. This is the width of the intervals, the subintervals, or the distance that the object travel from xi to xi plus 1. Distance. But this is just one of the subintervals, and our goal here is to calculate the total work done by this force. So we need to add all the intervals. So the total work is the sum of the works in all the intervals. W is equal to, it's approximately equal to I from 1 to n, f of xi star multiplied by delta x. And if we let n go to infinity, we get, it's not equal. If we let n goes to infinity, then this sum, this Riemann sum, will be equal to the integral of f of x dx from a to b. And this is how we get this formula. And this is also a type of methods. So in the future, if you have something that you can't calculate directly, you can, well, if in the future you have something that if you consider it as a whole, so for example, if you consider the work done by this force over an interval, but the force is changing, but you don't have any direct formula for it, you can try to first divide the interval you're interested in a lot of subintervals and analyze just one of the subintervals, or you can call it one of the elements of this thing. And we'll see this kind of example in the well, we'll see more examples that using this kind of methods today. So before that, let's do a simple example on calculating the work. Example 1, suppose we want to calculate, so suppose there is a particle that it's on the number line or the x-axis. And the force acts on this particle is determined by the distance between the particle and the origin. X. The formula of this force is given by x squared plus 2x pounds and we want to calculate how much work this force do. When this particle is moved from x to 1 from x to 1 to x to 3. So we have a force, but which is given by a function. It's a function depends on the distance. And we want to calculate the work done by this force if we move the objects from x to 1 to x to 3. From x is equal to 1 to x is equal to 3. So everything you need is here. You can just apply the formula directly. Apply the formula. Work. W is given by the integral f of x dx from a to b, where a is the initial location of the particle. In this case, x is equal to 1. So start from 1. And b is the terminate position of the particle. So in this case, it's 3. And f of x, this is the force. So it's equal to x squared plus 2x dx. So this is equal to the, just apply the formula directly. It's equal to 1/3 x cubed plus x squared from 1 to 3. So it's equal to 1/3 times 3 cubed plus 3 squared minus 1/3 times 1 cubed plus 1 squared. And this is equal to 18 minus 4/3. So it's equal to 50/3. Over 3. And the units of this, because the force is given by pounds, right? The force is given by pounds, and the distance is given by feet. So the units of the force will be equal to feet pound. And if another commonly used unit is when the force is given by Newton. Force, if the force is measured in Newton, the capital N, and the distance is measured in meters. The lowercase m, then the units of the work is joule. Is joule, or capital J. Any questions so far? Okay, let's see another example. So suppose there is a 200 pounds cable, which is 100 feet long and hangs vertically from the top of the building. So here we assume the building is tall enough, so then it's at least 100 feet high. And we want to calculate how much work is done or is required in order to lift the cable to the top of the building. This is still a work function, a work question or work example, but the problem of this example is that if we try to use the formula directly, we don't know what is if we try to use the work formula, W is equal to the integral of f of x dx from a to b, then we don't know what f of x is. It's not given by the example. So in other words, we don't know what is the, in other words, this is a cable, it's not a particle or an object. So I think in physics, you can try to maybe calculate its centroid and then calculate how much the centroid moved. But we are not going to do that in this class. We will use a different approach, a more calculus approach. So let's first try to draw this, try to picture the situation in this example. So we have a tall building, which is tall enough, and we have a cable that's hangs vertically on the from the top of the building. So it's about 100 feet. Well, it's exactly 100 feet. So the problem of this example is that the cable is a whole thing. It's not an object. It's not an object or a particle. There's not an obvious measure that for the position of the cable. However, if we just look at a small element of the table, so of the cable, suppose we are looking at this guy. Let's say this is a small element whose width is given by delta x. Then if delta x, so consider a small element, delta x element on the cable. Because the element is small, and it's small enough, so we can consider this element as a particle. So we can think of it as a particle. It's approximately a particle. And the work done, the work needed to move this delta x all the way to the top is given by the the work. The work needed to lift delta x to the top of the building is given by, let's use a lowercase w, given by the force that acts on this part, acts on the particle, multiplied by the distance that the particle traveled. So the force here, the only thing, in order to calculate the force, the only force here is the gravity. It's the gravity of this small elements. So in this case here, there's only one force that's there's only one force here. Actually, there are two forces here. One is the gravitation, the gravity of the elements, and the other is the force you move this particle all the way to the top. And this force is given by the gravity. It's the same. It has the same magnitude as the gravity, but it has a different direction. So just need to calculate the gravity, which is equal to m delta x g times d delta x. So it's the gravity. And this is the distance delta x traveled. So now imagine we split this whole thing, this cable, into a lot of subintervals, or into a lot of particle. Then, so again, if we divide this interval from 0 to 100, which stands for represents distance from the top of the elements to the top of the building. If we split this cable into a lot of elements, and suppose this is the ith element, it's right here, then the distance of the element delta x, or the ith element, can be described by a sample points. So the ith elements. So it's essentially the same thing, except here I divide the cable to a lot of elements and label them. And then the distance traveled by this ith element, you can use the sample points to represent it. So let's say this is xi star. So it's any points between xi and xi plus 1, because the element is small enough. So so they are approximately the same, xi star. In the meantime, the weight of the ith elements given by, so because it's 2 pounds per meters, right, wait a sec. So because the cable is a 200-pound cable, 200 pounds and 100 feet long cable. So the cable weighs 200 pounds divided by 100 feet. So the cable weighs 2 pounds per feet. And for the ith elements, because when we divide this cable into a lot of sub-elements, the width of each element is exactly delta x, or in the Riemann sum sense, it's the width of the subinterval. So this is approximately delta x times 2. And because we use pounds here, so this MIG is not, it's not really necessary. You can just use F of I. Gravity or the weights. Of the ith element. Both of them are essentially just forces, or a measurement of forces. And this is just the work done by lifting the ith elements. So in order to calculate the total work done, right, this is only the work done for ith elements. But when we divide the cable into a lot of elements, there are n of them. So therefore, the total work is the sum of the work done for each element. n to xi star delta x, and you let n go to infinity, which makes the delta x infinitely small, and so then it's practically a particle. And this is the Riemann sum. When you take the limits, the sum becomes an integral. The 2xi star is replaced by 2x. Delta x is replaced by dx. And the bounds of this integral is given by 0 and 100, which represents 0 as the elements on the top, the first elements, the distance of the first elements to the top of the building. And 100 is the last element. So here, this is 100. This is the distance of the last elements to the top of the building. So this guy is equal to x squared from 0 to 100. So it's equal to 10,000. And again, the units here are feet, pound. Feet, not pound. Any questions? Don't forget to unmute yourself if you have questions. So the idea here, essentially, is just if you see something complicated as a whole, then you should basically divide it into a lot of sub-intervals or sub-elements, or into a lot of elements, and then try to analyze one of them and compute the sums in order to compute the total effects of this thing. Let's see another example, similar. Suppose we have a tank which has the shape of an inverted circular cone. With height 10 meters and base radius 4 meters. And it is filled with water at first. Water to a height of 8 meters. And we want to find the work required to empty the tank. By pumping all of the water to the top of the tank. Top of the tank. Here we assume the density of the water is 10. It's 1,000 kilograms per meter square. Here is 1,000 kilograms. per meters cube. Yeah, per meter cube. And the gravitational constant is approximately 9.8 meter per second squared. So this this example is slightly different and slightly difficult, but you will see that the method here is essentially the same as the one we have done for example 2. So we start from the circular cone. It's a revert circular cone. And right. It's filled with water to a height of 8 meters. So up to here, this is the water surface. And we want to move this water out of the circular cone by pumping it up, pumping it to the top of the circular cone. And then we want to find the total work done by pumping this, just to empty this circular cone, to empty this water tank. 8 meter height. So again, there's no obvious way to do this directly or consider the water as a whole. So we can just consider small elements, for example, right. Let's again set up a coordinate system. Let's do this. Set up a coordinate system. And let's assume the top, again, the top is 0 and the bottom is 10. Right. And we divide this 0 to 10. So that x, the distance to the top of the tank. So essentially, you can consider this as a cable, but instead it's not. But at the beginning, it's not hang at the top of the building. It's hang like 8 meters height or 2 meters from the top of the building. So if we divide this into a lot of sub-intervals, right, and we shouldn't start from 0 because there's no water on the top. There's no water until x is equal to 2. So this is corresponding to the water surface, x is equal to 2. So if we divide this interval 2 to 10 into a lot of sub-intervals and consider the ith elements, or in this case, we should say it's layers. Right here. So it's just when we divide this, divide the interval into a lot of sub-intervals, then you can just think of, you just divide this water into a lot of sub-layers. And it's hard to grab here, but you get the idea. And if we just look at the ith sublayers, so suppose this is the ith sublayers. Correspond to the ith sublayers, xi plus 1. If we just consider the ith layers, Then in order to pump this layer, to pump it to the top of the building, to the top of the tank, the work done, the work needed to pump this layer to the top of the tank is given by, well, again, MIG. So this is the weights of the ice sublayer. And I use MIG here because it's measured in kilograms this time, multiplied by the distance traveled, the ice sublayer traveled. And the distance that this layer travel is just simply xi, or xi star. If you pick a sample points, any sample points between xi and xi minus 1, then the distance it traveled to the top of the tank is given by xi star. Now the problem is, how can we find the mass of this layer? G is just a gravitational constant. So if you look at this layer, when xi is x and xi plus 1, when delta x is small enough, then this layer over here with the top xi and the bottom xi plus 1, this layer is approximately a cylinder, a circular cylinder. Because xi and xi plus 1 are close enough, so the top, the radius of the top is approximately the same as the radius of the bottom. So it's approximately a cylinder, or in this case, a circular cylinder. But what is the radius? Or what should we use for as the radius of this cylinder? Okay. So in order to determine the radius of this cylinder, or find an approximation of the radius of the cylinder, we can use the similar triangles. So because because this is a circular cone, so when you cut it, the face you get, it's a triangle. And what's more important? Yeah, this is a right triangle. And then for the ith layer, right, this is still the intervals we are considering. For the ith layer, xi plus 1, xi, where we choose the sample points to be xi star. So for the ith layer, we can use the radius at x is equal to xi star. Use the radius at xi, at x is equal to xi star. So we use the radius at the sample point. And then because the top, the radius of the top of the circular cone is 4 meters. This is given by the question. And right, and the height of the corn is 10 meters. So this part, let's use a question mark for it. So by the relation of similar triangles, Ri divided by 4 is equal to the question mark, the length of this part, divided by 10 meters. And this question mark, because we choose the points, the radius at x is equal to xi star. So this part is simply 10 minus xi star. Because this thing here represents xi star. And xi star is the distance from this point to the top of the corn. And then from this relation, you get Ri is equal to 2/5 times 10 minus xi star. And right, and now the mass of the ith layer, Mi, is equal to the density of the water, which we usually use rho to represent it, multiplied by the volume of the ith layer. Volume. And the density is given by 1,000 kilograms per meter cube. The volume of the cylinder is given by pi Ri square multiplied by delta x. This is Ri square multiplied by delta x. This is the height of the I layer. And this is from how we divide the intervals into a lot of subintervals. And we have calculated that using the similar triangles that Ri is equal to 2/5 times 10 to the times 10 minus xi star. This is Ri. This whole thing square is the Ri square. There's a pi here, and then there's a delta x here. So the total work, well, the work for the ith elements or the ith layer in this example is Wi is equal to Mig times distance I, which is xi star. We have determined it before, and is equal to this is a complicated expression. It's equal to 160 pi times 9.8 times 10 minus xi star square times xi star times delta x. So if you're plugging everything in it, you get this expression. And this is 1568 pi. If simplify this, xi star 1568 pi times 10 minus xi star square times xi star times delta x. So this is the work done for the ith layer. The total work is equal to the limits of the sum of the work done for all the layers. I, and goes to infinity. So it's the limits as n goes to infinity of the sum of I from 1 to n of 150 1568 pi times 10 minus xi star square xi star delta x. And when you take the limits, the sum becomes an integral. The xi star becomes x, 10 minus x. Xi star becomes x. Delta x becomes dx. And the bounds for this integral will be from 2 to 10, where 2 stands for the distance, represents the distance of the top layer. So it's the distance of this layer to the top of the tank. Remember, there is a 2 meter difference between the top layer and the top of the tank, and 10 represents the last layer to the distance of the last layer to the top of the tank. Then once you plug in all the things, you get this integral. And if you keep calculating it, I don't have time for the details of this integral, but if you calculate this integral, you first simplify it and then use the formula, you get this is approximately 3.4 times 10 to the 6 joule. And we use joule here because we use the force, the Newton multiplied by meter. Any questions?
Could you just quickly go back to the last slide? I just missed one thing.
Okay. So if you don't have questions, we will meet next Monday.